Hey there, it's Katie with TutorPug, and I want to talk a little bit about polynomials today. First of all, you'll need to identify what is or isn't a polynomial function. Polynomial actually comes from the Greek poly, which means many, and nomial, which means numbers or terms in the mathematical sense. So this is just a combination of many numbers and letters that group together make terms, and polynomials play a large part in how the world goes round. So we've got lines are polynomials, quadratic functions, parabolas are polynomials, cubic functions are polynomials, so they're out there all over the place. The way you identify a polynomial is, sometimes it's easier to know what it isn't rather than what it is. There's lots of textbooks out there that will give you big, long mathematical descriptions, but the main rules are you cannot have any variables in a denominator. Numbers can be in denominators, but variables, x's, things that can change, cannot be in a denominator. That kicks us into a different type of animal other than polynomials. Variables cannot be under a radical sign. If you see a variable under a radical, it's not a polynomial. It's a radical function. So the location of the variable determines everything about the particular behavior of that animal that we're discussing. There will be no logarithms, no logarithmic statements in a polynomial. I guess technically you could have the natural log of 6 as a term, but there will be no variables associated with a logarithm in order for something to be a polynomial. Now, these can be a little bit hidden. Recall that a variable raised to a negative exponent means that variable is in a denominator, so that can be hidden. A variable cannot be in a denominator. It cannot have a negative exponent, which would indicate that it would be moved to a denominator, so it can be kind of hidden. Similarly, variables can't be under radicals. Sometimes they hide it and they don't put it under a radical, but you have a variable with an exponent that is a fraction, and that means, hey, I'm actually under a radical, which kicks you out of polynomial land. Pause. Begin. Here are some different functions that I just made up, and let's make a quick scan through and see which ones of these are polynomials and which ones are not. All I care about is what the variables or the x's are doing. I really don't care what the numerals are doing. So here I see a fraction, but it's just the number, and that's fine. 1/6 x squared, okay, that variable's not in a denominator, it's not under a radical, his exponent is a positive whole number, so this guy's okay. This one, 4 times the square root of 6x, well, again, I don't care about that being under a radical, I care about if this is under a radical. That x is not under a radical, he's not in a denominator, his exponent is a perfectly healthy, fine, positive 1, he's great. Pi's a number. Pi is not a variable. Pi is just a number. So it's going to sit there and say, hey, I'm going to be pi all day long. Every calculator in the world will give you the same value if you hit the pi key. So this is a polynomial right there. The whole thing all of it. All of his terms are behaving, so he's a polynomial. This one, right off the bat, x to the negative 4. X to the negative 4 is the same thing as 1 over x to the positive 4. So I just got a variable in a denominator, so the whole thing flunks. Sorry, you're not a polynomial. Doesn't mean you're bad, doesn't mean you're wrong. You have your place in math, that's fine. It's just not under the polynomial umbrella. This guy, 1/4, okay, that's fine. Numbers can be fractions. X to the 1/2, whoops, x to the 1/2 is the same thing as the square root of x. So I don't even need to talk about these other guys because, again, first term, flunks, you're not a polynomial. Quick comment over here, e times x. If this was a polynomial, e times x would be a safe term. E raised to the x is not a safe term. E as a coefficient, great. E as the base with x as the exponent, not great for polynomials. So you flunk because of the first guy. Pause. Begin. So when we're talking about polynomials, we have to have some vocabulary lined out. Vocabulary drives the world. You need to know that this is a pen and this is an eraser and this is a whiteboard so that we can communicate effectively. So these terms or these vocabulary items are really quite important, and they will continue to be important throughout your math career. I don't care if you're in Calc 4, differential equations, linear algebra. If you don't know what I mean when I talk about a term, we're not going to have a very long discussion. So I'm going to actually start here with term. A term is a clump of either numbers, letters, or numbers and letters multiplied together that when we group terms together, we make polynomials. So the number 4 standing there by himself, that is a term. It is a constant term. It's never going to change. But 4 by himself is a term. 4 times x is a term. I have a number, I have a letter, they're multiplied together, so that is a term. If I have 16x to the 72nd, that is a term. It is a standalone, by himself, number multiplied by a letter. The exponent checks out. It's not negative. It's not a fraction. This guy isn't in a denominator or anything like that. So this is a safe polynomial term. X standing by himself is a term. So think of terms as boxcars on a train. And we create polynomials by hooking boxcars together. So if I named this guy f of x, and I separated these terms with plus and minus signs, I have now created a polynomial. Polynomial is many of these terms grouped together. A polynomial can be one term standing there by himself. That's fine. That's a polynomial. It happens to be a monomial. It has one term. If I give it a partner, if I have 2 separate boxcars that are coupled together with plus and minus signs, now I have a binomial. Bicycle, 2 wheels, binomial. If I tack on a third term, I've got a trinomial. You can get up to quatrinomials or dodecanomials. You can just keep stacking terms together. Just keep making that train longer. So know what I mean when I talk about a term. Now let's back up and talk about the degree of a polynomial. The degree is like the point guard on an NBA team or the shot caller. He's the one that determines the ultimate behavior of that particular polynomial. So the degree of an entire polynomial is simply the biggest exponent, the value of the biggest exponent on a variable. So if I just have the number 4 as my polynomial or monomial, that has no x's, or I could actually think of him as x to the 0 power. 4 times x to the 0 power, because anything raised to the 0 power is 1. So if you just have a 4 standing there by himself, the degree of that polynomial would be 0. The degree of this polynomial, I look at my variables, I figure out which one has the biggest exponent. Okay, well, I only have one variable, and his exponent, if I don't see it, it's an invisible 1. Therefore, the degree of this polynomial is 1. A first degree polynomial is a line. It makes a line. This polynomial right here that I made up, let's give you a 3 just so you're not the same as that. The biggest exponent on a variable in this polynomial is 72. So his degree is 72. Even though that is not at the front of the line where he's kind of technically supposed to be by convention, the biggest exponent is the degree. So degree is going to come in real important when we start talking about end behavior and when we start talking about domain and range. Well, specifically range. So the degree is the largest exponent on a variable. Once you identify the degree, that degree means the whole term is now called the leading term. And if there's a positive sign out in front of that term, it's a positive leading term, and if it's a negative, it's a negative. Again, that's going to go into end behavior. It's very important. So this guy, for this made-up polynomial, the degree is 72. The leading term, even though he's not at the front of the line, would be negative 16x to the 72. And the leading coefficient would be negative 16, because a coefficient is a number out in front of a variable in a particular term. So this guy's coefficient would be 4. This guy's coefficient is negative 16. This guy's coefficient would be negative invisible 1. This guy's coefficient would be positive 1. So we care about the leading term, the degree, the leading coefficient. They all go together. And then we're going to have a discussion about the domain, the range, and then something called the end behavior. We're very concerned about what are the ends of a polynomial doing as it goes right forever and left forever. So by definition, one of the things that makes a polynomial is the domain will always be all real numbers. Negative infinity to positive infinity. Always. No matter what. I don't care what the degree is. I don't care if it's a 0 or a 1. It's, well, cut that last part out. Let's pick back up on domain. So the domain, by definition, is negative infinity to positive infinity. All real numbers, left forever, right forever, no matter what. And it really doesn't matter what the degree is. This guy's domain, you can put in anything you want for x. And if you're still unclear on domain, go back, search through my videos. I've got a couple that talk about domain and specifically when you have to worry about the domain. The range of a polynomial, again, range of anything, is how high does it go, how low does it go. And so on the range, this is something you'll just need to memorize. You'll need to learn. It's going to work every single time, but you need to learn it. If the degree of the polynomial is an odd number, if the degree of the polynomial is an odd number, pause. begin. So if I give you this polynomial, let's identify the degree, the leading term, the leading coefficient. The degree is 5. That's the biggest exponent on a variable. So that means the leading term is 2x to the 5th, and the leading coefficient is positive 2. If the degree of the polynomial is an odd number, 1, 3, 5, 7, 9, 13, 723, any odd number, then the range of that polynomial will be negative infinity to positive infinity. It will go down forever and up forever. If the degree of the polynomial is even, it will not be negative infinity to positive infinity. It will have a floor or a ceiling. If it's an upward opening polynomial, it will have a bottom, which would be a minimum. If it's a downward opening polynomial, it will have a maximum or a top point. And the range of that would be negative infinity up to the y value of that maximum value. And we'll talk about that in a different video. Odd, go wherever you want. Even degree, the range will be limited. It will have a floor or a ceiling. So now let's talk real quick about the end behavior. I referred to that briefly, but the end behavior is what happens to this polynomial as the x values go to the left forever or as the x values go to the right forever. So here are your options. The ends of that polynomial are either going to both go up, or they are both going to go down, or they're going to go in opposite directions. So you only have 4 options. You care about, is the degree odd or even? And additionally, you care about if the leading coefficient is positive or negative. So I always start with the even ones because on my hard drive, if I get run over by a bus and get put into a coma for 37 years, when I wake up, I am still going to be able to remember that this guy, a plain stripped down naked parabola, which is raised to the 2nd power, always opens up and the ends go in the same direction. That is written on the hard drive, and from that I can reconstruct the rest of my boxes. If the degree is even and the leading coefficient is a positive number, you're up, up. And that's how it goes every single time. If the leading coefficient is even, cut that out. If the degree is even, but the leading coefficient is negative, we're still going to go in the same direction, but we're going to go down, down. So I remember in my mind, okay, even, we're going the same way, and positive people smile, they go up, and negative people frown, they go down. Odd, think O for odd, O for opposite. So that's where we're going to go in opposite directions. And if it's odd and positive leading coefficient, it's up on the right side, down on the left side. And then if it's a negative leading coefficient, it flips. So those are a few things that we are really interested in when we're describing polynomials. We want to know the degree, the leading term, leading coefficient. Domain is always left and right forever. What's the range? Do we go up and down forever? Or do we top out at some y value or bottom out at some y value? So those things are really important to describe the behavior of polynomials. One other thing that we like to know are x-intercepts and y-intercepts. And this is a concept that will permeate the rest of math. I don't care what kind of function you have. To find the x-intercept or x-intercepts, if they exist, of any polynomial, you are going to set y equal to 0, or plug a 0 in for y. Pause. Begin. If I give you this polynomial, it's a polynomial, it passes all of our tests, no variables and denominators, etc., and I want to know the x-intercepts, the y-intercept, and the end behavior, and domain and range and domain and range. So I am going to go ahead, first of all, the degree is even, so I'm over here. The leading coefficient is a positive 16, even positive, so I'm up. And I'll just go ahead and describe the end behavior using mathematical language. This will stand for every end behavior. When you're describing the end behavior mathematically or using limit notation, the ends of a function have two different directions. It has a sideways or x motion, and it has a vertical or y motion. So when you are evaluating end behavior, you will always say, okay, as my x's go to the right forever, or as my x's go to the left forever, what is my function doing? Where is the height of it headed? Well, this guy, I know that he is up. So that means as my x's go to the right, as every single x value gets bigger, 10 to 11 to 15 to 20 to 97 to 432 to 6 million, as the x's get bigger to the right, that arrowhead is going up. So my y's are going to be getting infinitely bigger. And the way we say that is positive infinity. So this means go to the right. That tells me we're headed up. The limit on the other direction, again, on the bottom, we always describe the x behavior, the side-to-side behavior. As we go to the left forever, okay, we're even, we're positive, we're even, we're positive, we've got this box. Left forever, we're also going up. So that is how you describe the end behavior, either mathematically or using limit notation. I know that my domain, no matter what, is going to be negative infinity to positive infinity because it's a polynomial and that's the domain every single time. I'll worry about my range in a second. Let's find my x-intercepts and pause. Take that last part out. Let's find my x-intercepts and my y-intercept. So, to find the y-intercept, that is super easy. The y-intercept of any function on the planet is plug a 0 in to the function for x. So if I plug a 0 in for x, that whole term is going to go away or turn into 0. 0 minus 25 is negative 25. Please note, I have not picked up a calculator once. I am using some key little things that are on the hard drive to give me some information about what this function looks like in space. I'm going to graph it using my head and not using a calculator. So I know that it's going to go up. I know that it's going to hit the y-axis at 0, negative 25. Let's see where it hits the x-axis. Okay, to hit the x-axis, we're going to set the function equal to 0, or plug a 0 in for that output or that y. Pause. Begin. So if I do that, I have, and I can either factor this, it's a perfect square binomial, or I could use the square root property. I could add 25 to both sides. I could divide both sides by 16. And then I could take the square root of both sides. And I want to be kind of careful about that because when I take the square root of this, I need to remember that I'm taking the positive and the negative version. So x is positive 5/4 and negative 5/4. Square root of 25 is 5, square root of 16 is 4, and I need the positive and the negative version. So this guy, just a quick sketch, pause. Begin. Let's see, 5/4 is 1 and change, negative 5/4 is negative 1 and change. So I'm gonna hit the axis thereabouts. I'm going to, somewhere down here, when x is 0 and y is negative 25, I'm gonna hit the y-axis. And so I don't know exactly what he's gonna look like, but that gives me a vague idea. It gives me a real good idea of what he looks like. I could then do some additional math. I could figure out exactly where that bottom point is. That will come in a later video, but that shows you that using just a handful of pieces of information, I can draw a rough sketch of that particular polynomial without a calculator. So there's a quick trip through polynomials. Go practice these. Happy mathing.